Okay, let's try a few equilibrium problems. This is Dr. B, and let's start with some Le Chatelier type problems. We've got some dinitrogen trioxide, which decomposes, and it's endothermic. Predict the effect of changing the position of the equilibrium by doing various things. I'm saying to myself, adding reactant will shift it to the right. Taking away product will shift it to the right. I have one thing turning into two things, so pressurizing will not have the desired effect. You'll have to depressurize it to shift it to the right. And since it's since it's endothermic, heating it should help. So adding more N2O3, good idea. Shift it to the right. Adding more NO2, that should shift it to the left because it's a product. Increasing the volume decreases the pressure, and I already pre-analyzed that, and I said that's a good idea. Lower pressure should help. Lowering the temperature, I don't think so because you want to apply heat to this system since it's endothermic. That should shift it to the left. Another problem, consider the isomerization of butane to isobutane. It's got a reasonable equilibrium constant, and originally we're at 1 molar for the butane and 2.5 molar for the isobutane. Okay, so that we know some initial conditions, and they're going to say they add 0.5 moles of per liter of isobutane, and the equilibrium will shift to a new position. Now they've worded that kind of funny, but what I would do is say my initial conditions are after I have another half a mole per liter of isobutane. So I just start with it being 3 moles per liter, and I would figure out the equilibrium based on that, given that it has a K of 2.5. Well, let's see what we can plug in. Initially, butane is isomerizing to isobutane. They told us it's 1 molar and 3 molar respectively. Now, what would be the change to, if you're at that position, in order to get to 2.5? Well, this is your 3 is 2.5, right? So this would be 3 over 1. That's going to shift it to the left, right? So I think the butane is going to increase and the isobutane would decrease. Notice I had to do a quick Q versus K kind of thought there in order to do that. So at equilibrium, we just do the accounting. It's going to be 1 plus x, and this will be 3 minus x. Can we solve? Well, the equilibrium expression would be 2.5 equals that over that. So the 2.5 does equal 3 minus x over 1 plus x. If you cross multiply and work it through, you can solve that. And you'd find that x is 0.143. Now, I wouldn't recommend doing what I do here, set up a whole fresh ice table. It's just too time consuming. Just add 1.143 to this one and 3 minus 1.43 and resolve to get your K sub EQ. This should not be K sub P because we do have molarities. So KEQ, once we plug in our new numbers, is going to be still 2.5. They're not asking for that. They just asked for the concentrations of each when you're done. So those are your two answers right there. Not a bad idea to replug in to make sure it works. And it does. 2.857 divided by 1.143 equals 2.5. Relatively challenging problem by virtue of the fact they just don't give you initial and final. They say they add something. So finding the initial conditions, a little tricky there. 43b, if 0.5 moles per liter of the butane is added instead of isobutane, what is the equilibrium concentration of each gas? Maybe you could just say, well, it's going to be the numbers will be reversed, right? It's the same amount, but it got added to the other stuff. That would be a nice fast way to do it. But let's do it by the numbers. We have our initial conditions, which is going to be 3 for the isobutane. No, I'm sorry, it went from 1 to 1.5 for the butane. So it's now 1.5 for the butane because we added half a mole per liter, and 2.5 for the isobutane. And in this case, your Q is less than K, so you're going to lose some of the starting material. It's going to shift until it hits that 2.5, and you're going to add some product. So in this case, we do the math, and it's 1.5 minus x for butane, 2.5 plus x for the isobutane. Set up your equilibrium constant expression, which should be KEQ. And you can solve for x, which in this case is going to be 0.357, and the negative value. Interesting. So we subtract 0.357 from our 1.5, and it brings it down to exactly what we predicted, the same value but reversed, right? It's what the other stuff was. Plugging in, of course, gives us the exact same two numbers, and it worked. So in this case, it was q greater than k, and in this case, it was q less than k. And for 43b, we could have, like we said before, just done it by inspection and saved this whole pile of work. Okay, that is 3 more equilibrium problems.